reproductive matters or application to biological and neural systems. And our setup is define systems where we can define trajectories over different steps. We can think of either discrete time systems or continuous time systems in which we can measure the state of the system at some specific points. And we assume that the measured state of the system is n-dimensional. And we are interested in the case where we have a high dimensionality, either because of we have many degrees of freedom with n much larger than 1, or the case with long normal covariant dynamics with d much larger than 1, or both. And in this kind of systems, it's statistically impossible to infer the distributions of the forward dynamics and the backwards dynamic till that p. And for example, in binary systems, we will need 2 to the tn parameters to characterize the probability distribution. And in these cases, the KL divergence for estimating entropy production becomes computationally intractable. So our proposed method is to apply a non-equilibrium maximum max end optimization, which like a maximum caliber, in which we simplify the problem by recording a set of trajectory observables G of dimension D, and which in general G should be much smaller than the degrees of freedom n in the system. And we define dissipation from these observables as the minimum of the Kullback-Leibler divergence from some distribution Q to the backwards distribution tilde P, such that the expectations of the observables are constrained to the same value in distribution Q and distribution P. In principle, we are thinking of quite simple observables that are useful for estimating entropy production. For example, we found that it was useful in different problems to consider asymmetric time-lagged correlations. That is for case of t equal 1, in which we take two variables and we just look at the time-lagged asymmetric correlation. So measuring different of these observables, we can estimate this sigma g estimation of entropy production. And since distribution P already meets the constraints, it's trivial that sigma g is always going to be a lower bound of the true entropy dissipation, entropy production sigma. And in principle, it's not trivial to parameterize the distribution Q, but thanks to the remarkable properties of convex duality, maximum entropy problems, we can redefine the problem in a more tractable form, in which we introduce parameters theta, which are the Lagrange multipliers of observables G, and we find this equivalent form in which we turn the minimization a constrained minimization problem into an unconstrained maximization, in which we don't need to infer probability distributions anymore, but we only can find the solution just in terms of expectations. And well, a different way to interpret this is to describe the problem as decomposing the entropy production sigma into sigma g plus another component sigma orthogonal g, which is related with a maximum likelihood problem in an inverse maxent setup with a prior distribution tilde p and a likelihood p. So we defined sigma g as the KL divergence from distribution Q theta to tilde p, in which theta are the parameters inferred from minimizing the KL divergence between p and Q theta. And because of the structure of maxent problems, the distribution Q theta is going to be constrained within an exponential family in which we tilt the distribution tilde p by some exponential function of theta g until we find the distribution that is closer to p. And by this minimization of the maximum likelihood problem, we automatically guarantee that the constraints of the expectations is going to be the same. And this is the way in which the problem is simplified. And we also know that This maximum likelihood optimization can also be described or interpreted as the divergence between the backward distribution tilde p tilted by the instantaneous entropy production to the backward distributions tilted by the exponential of theta g. So in this way, we can interpret the product of theta g as the best linear estimation of the actual fluctuating entropy production. And we will find that the lower bound retrieves as the real entropy production if and only if we can find an expression of the fluctuating entropy production sigma in terms of a linear combination of the observables. So this is a nice way to interpret these bounds as the how much entropy production we can actually extract or infer from this set of observables. Interestingly, we can also relate this bound to variance-based TUR, so thermodynamic uncertainty relations. And so if we take the equation, this dual equation, and expand to a second order, we find this expression, and we can estimate theta from finding the fixed point in which the derivative becomes 0, and find just in the form of this equation, in which K is the covariance matrix of observables G under the backwards distribution tilde P, and solving this estimation of theta and plugging it again back into the original dual equation, we find this expression that reminds us of the form that we find in variance-based thermodynamic uncertainty relation, but we have a correction term which takes the form of this logarithm of the partition function of this exponential distribution. And interestingly, this lower bound, which we call hat sigma g, only requires solving a linear system. We don't have to do the full maximum entropy optimization. And it will retrieve the original bound sigma g when the product of theta g for the optimal theta has a Gaussian distribution. And we can interpret this as a generalized thermodynamic uncertainty relation in which this term, the logarithm of the average of the expectation of exponential sigma theta g, is a cumulant generating functional, which contains information about the variance, but also higher order cumulants. So in order to test the performance of these estimators, we compare them in two different systems. One is a non-equilibrium kinetic Ising model, in which we define spin flip probabilities using Glauber dynamics and applied sequentially. And we defined, so the interesting thing about this system is that we can, knowing the expectations of observables when they take these forms, we can estimate the true entropy production, just knowing the system's parameters. So we try to infer entropy production in this system for 1,000 spins using a sparse network with diluted connectivity in order to ensure that the statistics are highly non-Gaussian. And so we find that the classical quadratic TUR only work well when the system is very close to equilibrium. And the Gaussian estimator hat sigma g is good up to beta 2 when the statistics of the system start being highly non-Gaussian. And we find that solving the full max sense problem gives us a value of sigma g that captures entropy production very well, even at high values of beta, in which we are not, it's going to be very hard to observe the reverse transitions that we need for estimating entropy production. Also find that for free, we can also get estimations, the parameters theta that we obtain capture the asymmetry that's present in the original couplings in the system. So on top of the entropy production, we also get information about the structure of the system. And just to finish, we also tested this in a data set of neural data in Awakened mice from the NeuroPixel data set. We apply the sigma g estimator, and we find that we can discriminate between different conditions, mice in active tasks, or mice in passive, or just receiving other stimuli. And we analyze the connectivity structure of these parameters theta between different neurons, and we find that they at least appear to have an anatomically significant structure, like having clustering between different visual areas. And that's all. Thanks to my collaborators, Artemi and Sosuke. And we just released a preprint of the paper that you can find here. Thank you.
Thank you.